Okay, so we did the proof of the closure properties of regular languages under the concatenation operation and the union operation. And there's one operation left, regular operation left to prove, and then from this point on, then we can go ahead and do a whole bunch of other proofs, either by constructing from an NFA or from a DFA or the DFAs, or by invoking regular set operations. And I'm just going to go over the start operation first. We see an example of the start operation, and then we are going to go ahead and show a couple of other proofs for some other basic regular operations that would help us build languages off of other languages. So this last operation that we need to, or last basic operation we need to show its closure for regular languages is the star operation. The theorem states that the class of regular languages is closed under the star operation. The idea to perform this proof is just pretty much like the proof of union and concatenation. We assume that there is a regular language A sub 1, and we want to prove that its star, or A sub 1 star, is also regular. What we will do effectively is that we take an NFA, N sub 1, that recognizes the language N sub 1, and then we modify it in such a way that it will recognize the language A sub 1 star. If the resulting NFA accepts the language A sub 1 star, then from the corollary of 1.40 that we saw in unit in one of the previous units, we know that since now that a non-deterministic finite automaton recognizes A star, then A star must be regular. So the idea in this proof actually then comes along the same kind of processes that we have taken so far. We take the regular language, and of course its automaton. So suppose that exists some automaton like this that has a start state, and then it goes into a bunch of intermediate states, and it's an NFA, so it may have multiple arrows going out, and then it has a bunch of accept states. And by a bunch I mean 0 or more accept states. So if you call this N sub 1, then the idea is to build another regular language or another automaton, modify this automaton in such a way that it accepts the A star. So if you think about what the class A star is, if you remember, so A star was effectively, what was it? A star was the set of languages, strings W, such that, or rather W sub 1, W sub 2, such that each W sub I was a member of A, right? So basically what this means, what A star means, is that it basically takes or accepts a string that can be broken down into smaller pieces, each of which coming from the original language A. So effectively it's like a concatenation. And if you remember from the concatenation, if you had two languages, A sub 1 and A sub 2, and then you had their automaton, the concatenation would basically take each of those accept states and then plug them into the start state of the second language, right? And same thing if you wanted to concatenate 3 languages, then you take the second automaton, you plug all of its accept states into the start state of the third one, and so on and so forth. So that's basically the way that we prove the concatenation. All these, by the way, are epsilon transitions, right? So now if we want to create a language that accepts the concatenations of its own strings, the idea then would be to take each of these accept states to basically plug back into the original start state, and then since epsilon also belongs to the A star, then we wanted to also accept the epsilon transition. So effectively the idea will be, if this was my original automaton, then what I will do is I will basically add a new state here, make it the start state, and then so this effectively accepts the epsilon language, and then I plug that into my original automaton n sub 1 here. And so this n sub 1 effectively has a start state, this, so it goes in here, and then it has a bunch of intermediate steps and a bunch of accept states. And then what I'll do is that I'll make those accept states to move back to the start state with epsilon transitions, effectively kind of like concatenating it with itself in any number of ways. And I'll also, by the way, keep my accept states of the n sub 1 automaton, and this machine recognizes the language. So let's go ahead and do this informally and draw the description, and then provide the formal proof. And by the way, providing the formal proof is proof by construction, so we want to provide the formal definition of the modified automaton M, the modified automaton N. So then again, this is how my proof goes. I have an automaton. I have an automaton n sub 1. Actually, let's draw it kind of sort of horizontally. So if this were to be n sub 1, and n sub 1 will have a start state, a bunch of intermediate states, and then some accept states. And in this case, I'm going to represent it with like 3 accept states. Now I want to construct a new automaton that recognizes the star of this language. As I said, to do this, we basically, A star is effectively like any concatenation of strings from A. So basically, it should look the form of a concatenation. So remember, in the concatenation, concatenating two languages, and concatenating two languages, what we did is that we had epsilon transitions from accept states of A sub 1 to start state of A sub 2. So since we are now here concatenating our strings with itself, then the transitions you would assume, you would basically agree that the epsilon transitions from accept states are going to go back to the start state of my own language. Also, so this is number 1. Number 2 is epsilon is a member of A star, or rather A star contains also the empty string, which means that my new automaton N should have its Q sub 0 to be an accept state. So how do I go about doing this? Then here's going to be how my N, a constructed automaton, would look like. So for this automaton, I'm going to add a new start state, and I'm going to make that to be an accept state. Then I'm going to have my own little n sub 1 automaton that I'm constructing this off of. And so this had a start state, right? And then it had a bunch of intermediate states, and then it had some accept states. Let's represent those with 3, so remember this is now n sub 1. So in concatenating this, then I want an epsilon transitions to go from each of the accept states to the start state of my language. So then I would have all of my accept states of this combined language to have epsilon transitions into the original start state. So effectively what I did is that I used my own transition, my own automaton n sub 1. I had all its accept states transition with epsilon to its start state, so that way represents any number of concatenations. And then I also, since I need to accept the epsilon, I made a start state that is also the accept state. So then the modified automaton n recognizes the star of the language. So the L of n in this case then will be a star. So how does this look like? Oh, actually, let me just tell you a kind of an incorrect construction. It would be a bad idea to change. So let me actually do it this way. It will be a bad idea to use the original start state as accept state. So you may have actually noticed this, that in order for my language to accept the empty string, I added a new start state and I made that into the start state, and I made that transition into my original start state. It's actually a very interesting question. Why did we add a new state and made that a start state, and not just converted the n sub 1's own start state into an accept state? Because if we do that, the language certainly recognizes, or epsilon certainly would be a member of this language. The problem is that if we do it that way, if there is an intermediate transition here back to the start state, then that might introduce an undesired set of strings into my language, and I would like to avoid that. So that way, so for that particular purpose, if you want to look at and think about it more in detail and in depth, take a look at the exercise 1.15 at the end of chapter 1 from Seibser's book, and that exercise actually asks you to come up with a counterexample that shows that just changing the start state to an accept state would not be a desirable construction for this language. So that's one thing I wanted to note here before we actually went to talk about the proof. So now let's see how we can construct this language formally, or this automaton formally, to recognize the star of an operation, or the star operation of a language. So let's suppose that n sub 1 is the original finite automaton. So this will be the set q sub 1 sigma, the alphabet, delta sub 1, and then I call this q sub 1 0, the start state of my original, and then f sub 1, the accept state of my original language. And I know that L of n sub 1, or the language of n sub 1, is a sub 1, or that the n sub 1, the finite automaton n sub 1, recognizes language a sub 1. The q sub 1 effectively then will be q sub 1 0, q sub 1 1, q sub 1 2, and so forth, q sub 1 n. Sigma is going to be my alphabet. So I'm formally now defining this thing. So 2 sigma is the alphabet, and delta sub 1 is basically from set q sub 1 and alphabet over to q sub 1. And so effectively delta sub 1 of some q sub 1 I, comma, an alphabet will be q sub 1 j. This shows a transition function, actually a set q sub 1 j's, because it's a non-deterministic finite automaton. Actually, this is also epsilon. Oh, I'm wrong. Yes, you are absolutely quite right to laugh at me. It is a non-deterministic finite automaton, so this should go from q sub 1 cross epsilon over to the power set of q sub 1. And so then for every q sub 1i from q sub 1 and alpha from sigma epsilon, then that's going to happen. So the set of, or the transition of q sub 1i and alpha will go to a set of q sub 1j's. Okay. So then the start state of this guy is q sub 0. The start state is q sub 1 0, and of course I have the set of accept states. So the set of q sub 1I such that q sub 1I is an accept state. Okay, perfect. So now this is my construction. This is my original automaton. I'm actually draw a line here so that you would basically realize what I'm doing. So that is to construct the original automaton, and now I'm going to make my language or my new automaton. So new automaton n sub 1 is going to be an automaton, a non-deterministic finite automaton made of, again, the 5 tuple q, sigma, delta, and then q sub 0. This is now my q sub 0, the start state of my constructed or my modified automaton, and f, the set of its accept states. And I would want to pose that the language of n is going to be a star. So now I want this new automaton to recognize a star. So I need to construct it. So how am I going to do that? The first thing is to build its set of states. So its set of states is effectively q sub 1 union with my my newly added start state. So effectively, if you call this q sub 0, right, and then this is going to be q sub 1 0, and these are going to be q sub 1 i's from the accept state. So that's my the set of states. So basically what this means is that now the set of states of n is going to be the set of original sets q with the added q sub 0, which is now going to be my the n's start state. Notice that I did actually add a new start state instead of converting the start state of my original language, my original automaton, into an accept state. So sigma is the alphabet. Since it's basically the same language, the alphabet is going to be equal to the sigma. Let's call this sigma sub 1. And so I'm going to keep this same alphabet. So nothing added to it. Then 3. Then now the delta will be from the set q and sigma epsilon over to the power set of q. The start state is going to be my new start state. So the newly added start state. And finally, the set of my accept states, f, is going to be f sub 1 union with this newly added state, q sub 0. So that is going to be my accept states. So how will my transition be? So how would I define delta? What should this do? So delta basically takes all of the original delta sub 1s. So that's nothing really complicated. What we add to it, plus the added transitions to accept a sub 1 star. And what would those be? These will be a bunch of transitions, all the epsilon transitions to represent the concatenations, also the epsilon transition to effectively from q sub 0 to q sub 1 0, which is the start state of the original language, and the non-epsilon transitions that need to go nowhere effectively if they do not represent the strings in the A star language. So this is how I would write the delta sub 1. So actually let's do it a little bit more formally. So I say for every q being a member of, or rather call it q sub I, being a member of q, my own set, and for every alphabet symbol from the epsilon sigma, and remember sigma epsilon, and remember sigma epsilon is the alphabet union with the empty string or the epsilon symbol, then the delta sub 1 of q sub I and alpha is going to be a bunch of different kinds of transitions. And these different kinds of transitions are effectively these. If q is a member of q sub 1, or rather let's call this q sub I, is a member of q sub 1. Actually, let's take this subscript out because that's going to add to confusion. I'm talking about each q. So if q were a member of q sub 1, and also it wasn't a member of f sub 1, then that means it's one of these intermediate transitions. So there's nothing complicated to do that. I'm going to just follow the original transition for that. So it's going to take the delta q sub 1 and alpha. So it comes from the n sub 1. So I take delta sub 1 of q and alpha. Next, I'm going to now look at all those states that were the original start states, accept states. So if q was one of the original accept states, and the symbol that is processing is not or rather it's not epsilon, so for all the non-epsilon transitions from the accept states, I'm going to process them regularly as if they were effectively from the original n sub 1. Okay, so this ensures that I'm going to accept all of the strings that are from a sub 1. Now, what happens if q was a member of f sub 1 and also alpha was epsilon? Okay, just like the concatenation operation, here I'm going to do two things. Take the regular delta sub 1. Also take epsilon transition from q to q sub 1 0, the original start state. So then this will be basically the union of the original transition q and alpha from delta sub 1 if in fact my original machine had already an epsilon transition from its one of its accept states, union with q sub 1 0, which is just going to the start state. So this guy is q sub 1 0, the start state of your original machine. So you basically take epsilon transitions from the accept state, any of the accept states, onto the original start state as well. Now there are two more transitions to take care of, and that is if you are in the newly added q sub 0. So if q was equal to q sub 0, the newly added q sub 0, so there are two separate cases here, and alpha was epsilon. The second case is that if you are in the original state and alpha is not epsilon. Right? So if you want to think about it, you don't want to go anywhere except for an epsilon transition from the newly added q sub 0. So if that were the case, then if you were in q sub 0 and you're processing in epsilon transitions, you go to q sub 1 0. And if you were in q sub 0 and you were processing in non-epsilon transitions, then you go to the empty set. Basically, your newly added start state here is going to have only one transition, and that transition is going to be an epsilon transition. So this effectively constructs a new finite automaton, non-deterministic finite automaton, n, that basically represents a machine that accepts any string from n sub 1 because it processes delta sub 1s as you see here, as well as any concatenations of any strings from the n sub 1 because it has epsilon transitions from the accept states, all of the accept states, into the original start state, effectively representing any number of concatenations of any string that is already accepted by your language in any kind of format, in any number. And so this basically completes my proof. So this language that I created here is, or non-deterministic finite automaton I created here, is one that recognizes the star of my original language, and therefore the class of regular languages is closed under the star operation. Okay, so now that you've seen an example of, or the proof of the construction of an automaton, a non-deterministic finite automaton that recognizes the star of a language based on the original automaton, let's see a couple of examples. So let's say that we have language A sub 1, which is effectively the set of all the strings such that the strings W ends in A1, and that, let's suppose that sigma here is effectively set 0 and 1. So we want to basically show that, or rather build a deterministic finite automaton that recognizes the A star of language. So how are we going to do that? Obviously, we use our construction that we saw in the proof. So we suppose that there's an n sub 1 with q sub 1, sigma delta sub 1, q sub 1 0, and f sub 1. And so that machine is actually a fairly straightforward machine. This is a machine that has two states. And so effectively, if your machine sees a 1 as the last element, it's going to accept it. And if it sees a 0, it's going to return back to the start state. So this is q1 sub 0. This is going to be q1 sub 1. And so q1 sub 0 is your start state, q1 sub 1 is your accept state. So this machine, effectively, in this machine, q sub 1 is going to be the set of q sub 1 0 and q sub 1 1. And of course, your language sigma is 0 and 1, your alphabet is 0 and 1, and the delta sub 1 is going to be from q sub 1 and sigma epsilon over to the power set of q sub 1, which basically is something like this. If you draw the transition table, so with 0, 1, q sub 0, 1, 1, 0, and q sub 1, 1. So you stay in q sub 1, 0, you go to set q sub 1, 1, and then if you're in q sub 1, 1, you go to the empty set for 0 or 1. And the set of the start state is q sub 1, 0 is the start state. And the f sub 1, actually let me label these. Step 1, step 2, step 3, step 4, and step 5. F sub 1 is equal to set q sub 1, 1. So this is my original automaton, and so the n that I'm going to build is going to be a 5-tuple q sigma delta q sub 0 and f. So according to my transitions, my sets, q is going to be the newly added q sub 0 that I just add as a start state union with q sub 1. So this is going to be a q sub 0, a q sub 1 0, and a q sub 1 1. So again, to take a look at how this machine would look like, it's going to have a new start state, and the original machine is going to be something like this. and of course this is also going to be an accept state. So this is going to be the newly added q sub 0, this is q sub 1 0, and this is q sub 1 1. And so I'm going to epsilon transition from here to there, from here to there, just accept state transition. This is going to be my original transitions, and that is my machine n. So formally q is that set, the sigma is still the original sigma, which is going to be 0 and 1. Then the delta transitions are going to be from q cross sigma epsilon over to the power set q, power set of q, and the way that they look like, so for every q from my set q and for every letter of my alphabet from sigma epsilon, then the delta of q alpha is going to be a bunch of different delta transitions. So it's going to take the delta sub 1 of q and alpha if q was one of my original states and alpha was equal to was not and q was not an accept state. I'm going to take the transitions regularly. Then I'm going to also take the transitions regularly if q was an accept state from the original and alpha was not epsilon. Then if q was an original accept state right here, and alpha was epsilon, I'm going to basically then go back to the origin to the start state. So it's going to be q sub 1 0 union with the original transitions, because I may have delta epsilon transitions in my original language anyway. So it's going to go and take this form. Actually, let me be a little bit clearer in this case to avoid any kind of confusion. So I'm going to still, since q is one of the members of original machine, I'm going to basically do the original transition, union it with q sub 1 0. Basically, this is my epsilon transition to the start state. And then if q was q sub 0, which is this guy, and alpha was epsilon, then I'm going to go to q sub 1 0 0. So that's this transition. This transition, actually, let me draw it with a different color. So this transition is this one, and this transition is this one. So that's that guy, and this is that guy. And finally, if q was q0, if I was here and alpha was not epsilon, so for all the other transitions, q sub 0 is not going to have an outgoing transition. For all the other letters, this q sub 0, the newly added state, will not have any outgoing, so it's going to go to the empty set. And so then my now q sub 0 is going to be the start state, and the f's of the new language or the new machine is going to be f sub 1, which is the start states, accept states of the original machine, union with this newly added q sub 0 that I added. So this guy and any of the start states of my, or the accept states of my original machine, are going to be a an accept state. So let's look at this language. What kind of so n sub 1, what kind of languages does this recognize? So if it's a 1, it's going to be recognized. If it's a 0 1, it's going to be recognized. If it's a 0 0 0 1, it's going to be recognized. So it's actually, in this case, I think this language, this machine recognizes a W that has the form of 0 star 1, right? So if it has a bunch of zeros and then a 1. So what does this machine recognize? This machine, N, recognizes epsilon, because epsilon it starts in an accept state, so it recognizes epsilon, and it also recognizes a 1 or any combinations of 0 and ending in 1s that also end in 1. So it also recognizes a 1, it recognizes a 1 1, it recognizes a 0 1, it recognizes a 0 1 1, and so on and so forth. So if you have a string that can be split into strings that the original language recognizes, then this newly constructed machine will recognize those as well. Notice one quick thing, that this machine, if I look at my original machine, and so the original machine is looks something like this, right? So you've got your q sub 0, q sub 1 0, and your q sub 1 1, and so this is my original machine n sub 1. So notice that it would be a mistake actually if I made this q sub 1 0 a start state, and then I added the epsilon transitions. Notice this will result, so this machine results in the wrong language. Why? Because now this machine does accept epsilon, so this accepts epsilon, but also accepts 0, right? Or 0 0 0 0, because see, this transition, any number of zeros transitions into an accept state, which is so these are not in A star, right? So this is a counter example, and remember earlier I talked about this the idea that it would be a bad idea if I just changed the start state to an accept state instead of adding my own new accept states like I did here. And so see here, I added my own accept states instead of just converting the start state to an accept state, and this is precisely the reason that we want the A star or the N to recognize the epsilon, and so we know that epsilon is recognized by a machine in which the start state and the accept state, the start state is one of the accept states. But if we do that by just simply converting the start state of the original machine into an accept state, we are actually introducing a bunch of wrong strings to this language, and that is precisely why we added a new start state, q sub 0, as we did up here. So then again, basically, if you're asked to create a machine that recognizes the star of a language, you basically create a machine for the original language, and then what you will do is that you'll add a new start state, and then you make that new start state an accept state, and then you make transitions, epsilon transitions, from these accept states onto the start state of your original machine, and then you keep all the original transitions the way they were. And so basically your new set of states is going to be the union of original states and the set of original states and the new start state you added. Your epsilon transition is going to be a 5-step transition that you see here on the right hand side of this board. Your newly added state is going to be the start state, and then you will add that in the set of accept states for your machine to recognize. So this is one example of a machine that recognizes the star of a language.